Is screen visible?
Yes, sir.
Okay, thank you. So in our previous lecture, we have discussed about the modulation index. If modulation index is 0, it means the carrier wave is unaffected in terms of its properties, characteristic properties, that is amplitude, phase, frequency, position, width, etc. Modulation index generally lies between 0 and 100%. For 100% modulation, the amplitude of the carrier wave and the modulating signal are the same. If modulation index increases 100%, that will be called as overmodulation. And overmodulation results into the distortion. In our previous lecture, with the help of certain diagrams, we explained the 0% modulation, the 100% modulation, and more than 100% modulation that leads to the distortion of the modulated signal. We also discussed about the power content in the amplitude modulated wave. There we discussed about the total power in modulated wave, carrier power. The ratio of this is equal to 1 plus modulation index square divided by 2. We also talked about the current in the modulated wave and the carrier wave. IT represents the current in the modulated wave and IC represents the current in the carrier wave, and the ratio of total current, that is modulated current divided by carrier current, is equal to square root of 1 plus MA square by 2, whereas MA is the modulation index. In the end, we discussed some numericals based upon the power and current. So in continuation with that, we will today also solve two more numericals based upon the modulation index, the total current, total power, etc. So let us start today's lecture. Another numerical, the antenna current of an amplitude modulated transmitter is 10 amperes. It means this 10 ampere is the modulated current, that is IT1, when it is modulated to depth of 30% by an audio signal. Depth 30% means the modulation index is 30% and the modulation will be 0.3, that is 30 divided by 100. We get the modulation index. It increases to 11 ampere when another signal modulates the carrier signal. Here, then we have the second signal modulates the current to 11 ampere, means current has increased by 1 ampere due to the second signal. The first signal results into the modulated current is equal to 10 ampere with modulation is equal to 0.3. Second signal changes the modulated signal's current by 1 more ampere, that is 11 ampere. Then what we have to do, we have to find the modulation index due to the second signal. So we are given with the conditions for first signal, the modulation index for first signal, the total current for the first signal. We know the expression for the total current divided by the carrier current, which is equal to 1 plus MA square by 2. Here we are not writing MA. Here if you can see, in this we are not writing MA. Here we have written M1 because this is the modulation for the first signal and the modulation index for the first signal is 0.3. So substituting the value of IT1, that is first signal modulated current, that is 10 ampere. Then carrier wave we have to find from above expression. So we will get IT1 divided by 1 plus M1 square by 2. M1 is 0.3. So on substituting the value of total current in the modulated wave due to first signal is 10 ampere divided by 1 plus modulation index 0.3 square divided by 2 square root. So carrier current here comes out to be 9.78, and in modulation we know the carrier amplitude will remain the same, that is 9.78 ampere. Now in the second case we have the second signal, and the second signal is superimposed upon the first signal. So here once again we have to make one more change. here instead of writing M2, we will write MT, that is total modulation. Total modulation due to first signal and the second signal. So here we can, from this expression, we can find the modulation index due to the both signals from the above expression, which is equal to MT is equal to twice ratio of second signal modulated current divided by carrier, which is fixed for both the signals, square minus 1. So IT2 we know is 11 ampere, carrier current is 9.78 ampere minus 1, and in this way we get the total modulation index due to both signals. So what we have to find? We have to find the modulation index due to the second signal. So modulation due to second signal is given by total modulation is equal to sum of the squares of modulation due to first signal and the second signal and square root of that sum. So to find the M2, we have to rearrange the terms in equation second, and M2 will be equal to total minus M1. Total is 0.73, M1 is 0.3. So 0.66 will be the modulation index for the second signal, and percentage modulation will be 66%. So let us solve one more numerical on the same pattern, that is two signals. The antenna current of an amplitude modulated broadcast transmitter modulated to the depth of 40%. So it means for the first signal the percentage modulation is 40% and modulation index is 0.4 by an audio sine wave 11 ampere. So here we are given with the 0.4 modulation index for the first signal, and current in the modulated wave of the first signal is 11 ampere. It increases to 12 ampere when a second signal is used. It means the modulated wave after the second signal, the current increases by 1 more ampere, that is 12 ampere. Then again we have to find the modulation index due to the second wave. So it is on the same process. So first what we do, we will find the carrier current due to the first signal, which comes out to be 10.58. Then we will find the total modulation index, just like the previous example. After finding the total modulation index, we will again make use of the expression in which we can find the total modulation index due to two signals is equal to sum of the squares of the modulation index due to first signal, second signal, and the square root of that, and we get 0.6407 modulation index and 64.07% modulation index. So this numerical and the previous numerical are on the same pattern. You can do it yourself when I send the class notes after 1 or 2 more lectures. Just after the completion of Unit 1 Part 1, I will send the class notes. You can see from those notes these numericals and practice them. Now the next topic of our syllabus is the power content in an amplitude modulated wave. So power content is obtained from the expression of modulated wave, modulated signal. That is, modulated signal is a sum or superposition of the carrier signal, carrier wave, or message signal, that is modulating signal. So carrier power is obtained by making use of the carrier signal and taking its mean square value. Mean square value means integration from 0 to 2 pi. Why integration from 0 to 2? Because our signal is sinusoidal or cosine function, trigonometric function. So the repetition of the function is over 0 to 2 pi, or we can say that period of the signal or sine or cosine signal is 2 pi. So that's why we have used in integration the limits 0 to 2 pi, and the carrier signal is given by a cos omega ct. Its square, this is the mean square value. To find mean square value, we have to integrate it over 0 to 2 pi, that is its period. For any function, if we want to find the mean square value of that function, then we have to square the function and we have to integrate that function over its period. If period is 0 to time t, then integration will be 0 to t. If period is twice t, then we have to integrate 0 to twice t. But here
सर वॉइस नहीं आ रही आपकी।
हेलो
सर वॉइस नहीं आ रही थी, बीच में कट हो गई थी।
अब आ रही है?
यस सर अब आ रही है।
Okay. Whenever we want to find the mean square value of any physical quantity, the process is to square the physical quantity and then integrate that physical quantity over its period. For example, a function has period 0 to t, then we have to integrate 0 to t. If function has period 0 to 2t, then we have to integrate 0 to 2t. Now the function, now we are dealing with the modulating signal, carrier signal and modulated waves, and all these are nothing but the sine or cosine functions, and we know for the sine and cosine functions the period of repetition is 0 to 2 pi. That's why we have integrated equation 3.37 from 0 to 2 pi. This is the equation. So the value of this integral we have to remember, and the value of this integral is half a square. Capital A is the amplitude of the carrier. Now similarly, the power in the sideband, again the power will in the sideband can be obtained by integrating the term which is responsible for the sideband, and this is the modulating signal xt cos omega ct. So we square it, mean square value of xt cos omega ct. Again we have to integrate it over its limits. Limits of the trigonometric function sine cosine function are the 0 to 2 pi. So again we are making use of one more trigonometric identity, that is cos square omega t theta plus cos square theta is equal to 1. That is an identity. Cos 2 theta can be written in terms of the sine and cosine terms also. So here twice cos square theta is written in terms of cos 2 theta t. So that will be equal to 1 plus cos 2 theta t, that is equal to twice cos square theta. So we have substituted that value. Now, in modulation technique, we generally use a filter to eliminate the last term. This is the second term which is present in the expression. So the second integral in equation 3.18 is eliminated with the help of some filter. So when we use the filter, the second term will be cut off, will not pass with the message signal, and the power due to sideband will only be due to the modulating signal, and it is written as half x square t. Bar means mean square value of the modulating signal. So what will be the total power? The total power will be equally divided into lower sideband and the upper sideband. So total power was equal to PS, and it is divided into two equal halves. So it will become half of the sideband power. Sideband power is equal to half x square t. That is equation 3.39. So the sideband power in lower sideband, sideband power in upper sideband is equal to half of the power of the sideband, that is half x square t. So it will become 1/4 x square t. X square t bar means mean value of the modulating signal. So what will be the total power? Total power will be the sum of the carrier power and the sideband power. Carrier power is equal to half a square, and the sideband power is the half x square t bar. Now let us move to the next topic of our syllabus, that is double sideband suppressed carrier. Sometimes in the modulating signal, we do not want the carrier wave with the message signal. So why we don't want the carrier wave with the message signal is explained in this method, double sideband suppressed carrier. As the name says, suggests suppressed carrier means the two bands will be present. Lower sideband, upper sideband will be present, but there will be suppressed carrier, means the carrier wave which was originally present in amplitude modulation will now be absent. So now here what we are doing, we are shifting ourselves from amplitude modulation technique to a newer technique that is called as double sideband suppressed carrier, that will have two sidebands, but unlike amplitude modulated wave, in Dspsc, the carrier wave is suppressed. And why carrier wave is suppressed, we will learn it in this slide. So let us start with the Dspsc equation. We have already discussed the Fourier transform, frequency shifting theorem, and how to use the frequency shifting theorem. We obtain shifting in the frequency by plus minus omega m quantity. And modulating signal is the sum of the carrier wave. First term represents the carrier wave, and the second term represents the message signal, that is small m. And this message signal is in the frequency and time domain both. And this frequency first term in the message signal represents the upper sideband, second term represents the lower sideband. So equation 3.77 can be divided into two parts. The first term, A cos omega ct, is the carrier term, carrier wave equation. Second term is the message signal, modulating signal. This message signal or modulating is the Fourier transform to suppress this. We have a xt, that is message signal, and we have capital X omega is the Fourier transform of the message signal. In our previous amplitude modulated wave, we have made use of Fourier transform and frequency shifting theorem. So here also we will make use of the Fourier transform property, that is frequency shifting property of the Fourier transform, according to which if we multiply a function by an exponential term, exponential j omega ct, then we will have a function in the frequency spectrum with the condition that its frequency is shifted by minus omega c. In the same manner, if we multiply a modulating signal with a function that is exponential minus j omega ct, then this function xt will transform into a function that will be frequency dependent, but with the change in frequency, that is frequency is increased by an amount equal to omega c, and omega c is the frequency of the carrier. Now we know that the message signal is written as xt cos omega ct. You can see it from the previous slides. In amplitude modulated wave, the message signal is written in terms of the xt cos omega ct, and we know that cos theta can be written in terms of the exponential function. We have already made use of this expression in the amplitude modulated expression for the frequency spectrum or time domain to frequency domain analysis. So here, substituting for the cos theta t, that is cos omega ct, we can write it as exponential eta theta plus exponential minus eta theta divided by 2. Similarly, we can also write sine theta as e raised to power eta theta minus e raised to power minus eta theta by 2 eta. So these are the representation of sine and cosine functions in terms of the exponential functions. So now we will replace the cos omega ct in terms of the exponential function, that is e raised to power j omega ct plus e raised to power minus j omega ct divided by 2 is equal to cos omega ct. So now further we also know that if we multiply a modulating signal xt e raised to power j omega ct, then the time domain modulating signal will change into frequency and modulating signal with frequency lower by omega c. If we multiply xt by e raised to power minus xt, then again we will transform the function from time domain analysis into a frequency domain analysis. frequency domain with the frequency omega c from the carrier signal. So on substituting these values, half xt e raised to j omega ct, half xt e raised to minus omega ct. Now we can replace these quantities with capital X omega minus omega c, is the function in frequency domain, the lower frequency component, which represents the lower sideband, plus X omega plus omega c, which represents the function in frequency domain, and function with higher frequency component, that is upper sideband. So we can say that xt cos omega ct represents the double sideband suppressed carrier signal. In this expression, we don't have any wave equation for the carrier wave, and in this way we have suppressed the carrier wave in the modulating signal expression. Now the block diagram for the same. As we know, we have to have a function xt, which is modulating signal, which is called as baseband signal. We have to multiply it with cos omega ct. This is achieved with the help of a product modulator, which is again an electronic circuitry, which will multiply the two signals. Cos omega ct is a signal, xt is a modulating or baseband signal. When these two are simultaneously fed into a product modulator, this product modulator will multiply the modulating signal with the cos omega ct, and we will get a modulator, and this modulated signal is called as the double sideband suppressed carrier. This is here I am talking about this xt cos omega ct, which is the output of a product modulator, which have multiplied the modulating signal and the cos omega ct. This modulated signal is called as double sideband suppressed carrier because this expression does not have any carrier wave equation, just like the amplitude modulation. Amplitude modulation has the carrier wave equation, but double sideband suppressed carrier does not have the carrier wave equation, and hence the name is double sideband suppressed carrier. Now few points related to double sideband suppressed carrier, that whenever the signal crosses the zero, the envelope will change its shape. You can see here the red line, the modulating signal is changing at this point, at this zero. At this point, the modulating signal is also changing its shape. The second thing which is not present here is impulses are missing in double sideband suppressed carrier. Further, the bandwidth of the signal is equal to upper sideband frequency minus lower sideband frequency, and this comes out to be twice omega m. The bandwidth for the double sideband suppressed carrier is same as that of amplitude modulated wave. For amplitude modulated wave also, the bandwidth was twice the highest frequency in the modulating signal, and this is the same for the double sideband suppressed carrier also, which is the bandwidth equal to twice the highest frequency in the modulating signal. So this is all from my side for today's lecture. So